All right, everybody, it is 4 o'clock. Welcome and hello. I hope that you had a nice weekend and are ready to rock and roll for another big week of number theory here. Sorry, I forgot to send you an email. Usually over the weekend I do with just a little preview of what is coming in the coming week, and I just sort of it slipped my mind to do that. This week is just basically a carbon copy of the first 2 weeks, which is that there's an assignment due on Friday at the end of the week. That's based on the stuff we're doing now on congruence theory primarily. And we're going to be talking about that all week, really. So right now we're looking at sort of one linear congruence and trying to solve it. As we get later into the week, we'll throw in a whole system of congruences and think about trying to solve that. And look at some variations as well. So maybe some congruences that we want to solve that are not linear. So there's, of course, ways we can make this problem harder on ourselves. And we'll get to that, but we didn't really quite finish, at least from my perspective, I wasn't totally satisfied that we had quite finished everything that we should say about this section. By the way, this is in section 4.4, which I think is the third of the 3 sections that the homework is covering. So if you want, you certainly can get started on any of that assignment after today's class if you haven't started already. But I'm just going to recap what we had left off with on Thursday last week, which was this theorem, which is basically it's really the central result about solving linear congruences. And so it's kind of the main event here. But what we didn't do last time is show any kind of an example of this. So I would like to do that today. Before I get into that, does anybody have any questions about anything, really? I guess I could just remind you, we are now into the 4th week. On the Canvas website, there are practice quizzes now, pretty much every week. So there was one for the first 3 weeks. So if you haven't looked at that yet, that'd be, if you're looking for something to sort of practice and test your knowledge on, you could try that. Those are not supposed to be long. They're all just kind of like 1-page, little mini quizzes to just allow yourself to see where you're coming along with the material. And so then at the end of this week, there'll be another, practice quiz for week 4. We have our first midterm on Tuesday, March 3rd. So that's actually right at the beginning of week 7. So we're about halfway to the first midterm from the start of the semester. And we only have 2 exams in this class before the final. So it will be fairly substantial. At some point, I'll talk much more about the exams and give you some resources and some things to practice and study. So I think we're a little early for that yet. Just still trying to get through some of this basic material, which some of which is probably still a little bit review for some of you. Certainly the Math 302 would be relevant, maybe not quite in this much detail, working with systems of congruences mod n, but this by and large should be relatively familiar notations and concepts and so on. At least I'm hoping. If it's not, let me know so I can make some adjustments here. So anyway, if there's no questions so far, I'll just remind you about this central theorem in this section. We're going to take, the linear congruence is right here. AX congruent to B mod n. And the goal, of course, is to solve for x. And that will be a solution modulo n. So we have to understand that when we're in mod n, there can be many congruence class representatives for a solution. And what we're really interested in is just one representative for each non-congruent solution, if that makes sense. So if I'm working in mod 100 and I say that 3 is a solution to my congruence, that's not different than 103 or 203 or 303. Those are all to be viewed as just one solution, right? In other words, those would all be mutually congruent. What we're really interested in here are the mutually incongruent solutions, the ones that really are not equivalent to each other modulo n, right? So this theorem is going to try to tell us something about that. We take this linear congruence, AX congruent to B mod n. Our goal is to solve for x. The first question is, does it even have a solution? Okay, and to decide that is very straightforward. We simply take the greatest common divisor of A with n and I'm going to call that D for a moment, as long as D divides B. Okay, so notice that this condition really involves A and B and N. All three variables are involved here because the D involves A and N, and the GCD of those numbers has to divide B. Okay, so this is the result, that there will be a solution if and only if D divides B. And if there's a solution, then it turns out there's not just one solution. Okay, so you sort of open up the floodgates at that point, and in this case, there are actually D mutually incongruent solutions. So again, that's what I'm interested in. I'm interested in incongruent solutions, not a bunch of solutions that are all just essentially the same in mod n, right? So I'm looking for D solutions in mod n that would be viewed as different in mod n, mutually different from each other, okay? So this theorem says that there are D mutually incongruent solutions. And actually, this is one of those theorems that more or less is proved by just producing them. You know, you basically produce the solutions. How do you produce the solutions in the first place? Well, we talked about that last Thursday. The idea is that this congruence can be re-expressed as, you know, n dividing ax minus b, and then that can be re-expressed as saying that ax minus b is equal to, say, n times k. K is some integer. And so then that can be re-expressed, sorry, I'm kind of scribbling in the corner over here. That can be re-expressed as this Diophantine equation. So the unknowns in this Diophantine equation are, of course, the x that was already the unknown in the original congruence. And now we have introduced, this is a k, I barely have room to talk about, but k is some integer multiple of n here. Sorry, the k is some integer that gets multiplied by n to make this equation true. So you have a Diophantine equation, which you can then solve by methods we learned in chapter 2. So you're going to solve for some x naught. So x naught is some specific solution that you find to this Diophantine equation by the methods we studied in chapter 2. And then once you have that solution in your hands, then you can build actually a comprehensive list of all D of these mutually incongruent solutions that are listed here. So I've made the list right here. Okay, so x naught minus n over d, x naught minus 2n over d, and so on and so on. And of course, d divides n. So everything you're looking at here is an integer, even if it kind of looks like a fraction. It's actually an integer. And so essentially, well, the other thing I wanted to point out is that if x naught is a solution, so if that's the first one that you found, the next closest equivalent, or in other words, congruent solution in mod n would be x naught minus n. So these would, of course, be in mod n equivalent to each other, right? But actually, if you look at how far you are from this first solution to this last solution, you haven't even made it to x naught minus n. Look what you're subtracting. You're subtracting multiples of n over d, and you're not even getting to d over d times n. So these solutions that are here are somehow sandwiched strictly within this range. What I hopefully am convincing you of, without writing a whole lot down, is that none of these are congruent in mod n to each other. If I wanted something that was congruent to x naught in mod n, this would be the first thing I would think of. And all of these solutions that are listed here are closer to x naught than even that distance. Yeah.
It's the same as x naught plus n.
And plus n, yes, absolutely. Plus or minus, doesn't even matter. Yeah. I was using negatives here. These negatives, of course, come about because of the minus that's in the Diophantine equation here. Yeah. So what I hopefully have convinced you of is that this is a list of D things, right? You can just count them. It's D things, and none of them are congruent to each other in mod n because none of them are far enough apart to be congruent in mod n. So these are D incongruent numbers, And they will all solve this congruence. Because if A x naught is already a solution, if you have already found x naught as one specific solution, then if you decide that you're gonna go back and plug in, let's just do the first one here, n over d, right? What is that going to be congruent to? Well, that will be congruent to ax naught minus an over d. And so ax naught was given as b, and an over d is actually a multiple of n. Because d divides a, right? D is a greatest common divisor of a and n. So d actually divides a. So what you're actually subtracting off of b right here is a multiple of n. Meaning that in the world of mod n, you're actually subtracting nothing. So this guy right here is also a solution to the same congruence. And you can check each of these as being a solution. So have I convinced you? There's d things in this list. They are all mutually incongruent to each other, and they are all actually solutions to our congruence here. Yeah. And these all arise when we actually solve this Diophantine equation. Okay, so just wanted to recap this theorem. But the other thing I want to do, which I didn't do on Thursday, is actually just do an example with you. Okay, so let's practice this this result. I'm going to come over to this next board here. Try to keep this thing from teetering over. So let's do an example. Let's solve the congruence 34x is congruent to 60 in mod 98. 34x is congruent to 60 in mod 98. So suppose that that comes across our radar and we would like to solve this one here. The very first thing I should do is just see if it has a solution. Okay, that's the first part of the theorem. So I'm going to figure out the GCD of A and N. So for my solution here, right, the GCD of A, which is 34, and N, which is 98. We can probably figure this one out more or less in our head. It turns out that it is actually just 2. Of course, if you don't know what the GCD is, just glancing at it, then we have our whole Euclidean algorithm that we can use to come up with that GCD. And in fact, we are going to need to use that Euclidean algorithm anyway. So I guess I was sort of just jumping ahead here to this value, but we'll need that Euclidean algorithm in the solution, as you're going to see. But for the moment, I'll just take it as for granted that this is equal to 2. And sure enough, that does divide 60. So the D does divide B, and we would be expecting 2 incongruent solutions mod 98. So let's just write that down. By theorem 4.7, there are 2 mutually incongruent solutions in mod 98. Again, it's incongruent solutions that we care about. If I want congruent solutions, there's infinitely many. You find one and then just add 98 till you're blue in the face, and you just have a whole bunch more congruent solutions. As there'd be an infinite number of those. Okay, so now how do we get these 2 mutually incongruent solutions? That's the next part of it. So I'm going to use the Euclidean algorithm on 98 and 34. So watch this. I take 98 and I divide it into 34. It goes 2 times into 34, leaving me a remainder of 30. And you guys hopefully won't get too bored with me on this. This is just the Euclidean algorithm, but I do need to go through every step. 34 gets divided now by 30, goes in there just 1 time with a remainder of 4. And next we take 30 and we divide that by 4. It goes in 7 times and leaves me a remainder of 2. And then finally the previous divisor becomes the new left-hand side, which is 4, which is 2 times 2 plus 0. And as you know, the GCD of the two numbers is the last non-zero remainder. But what we really need to do here, slow me down, by the way, I guess if I go too fast, I get excited. What we really need to do here is run this algorithm backwards and write 2 as a combination of 98 and 34. Right? I mean, ultimately, we really want to write 60 as a combination of 98 and 34. But the first step to doing that is going to be to write 2 as a combination of 98 and 34. So I'm going to start with 2, and I'm going to run my algorithm backwards, right? So 2 is 30 minus 7 times 4. And now I replace 4, which is my previous remainder. I'm going to replace 4 with 34 minus 30. Before I go any further with back substituting, I'm going to clean this up, just simplify the values a little bit. It looks to me like it's actually a total of 8 factors of 30 minus 7 factors of 34. And at any given step, of course, we should be able to check our work that this is actually correct. Okay, now I'm going to go to the next line here, and I'm going to replace 30 with 98 minus 2 times 34. And then we have still subtracting 7 times 34. Okay, and so let's just see where we're at with that. That's 8 factors of 98. And then it's actually minus 23 factors of 34, if I did that correctly. Okay, so far so good? All right, so what does that actually tell me? I'm going to eventually want to go back to working in mod 98, right? So what we have is an equation, which is that 2 is equal to 8 times 98 minus 23 times 34. Just to kind of summarize what our calculations gave us. This is the first step. Write your GCD as an integer combination of the n and the a. Right. And from here, we can pass to mod 98 if we want to. So I can say, so then 2 is congruent to negative 23 times 34. And that would be in the world of mod 98, because in the world of mod 98, of course, 98 just becomes 0. So I've got my 34 times something equal to 2 in the world of mod 98. But as I said before, we ultimately need 60 here. So what you have to do now is simply, well, if D divides B, then you should be able to scale it up by whatever that multiple is. So 2 divides into 60 with a quotient of 30. So I'm just going to multiply through by 30, right? So multiply by 30, which is actually, I'll just write it out as 60 over 2, which is 30. And that will give me 60 congruent to, now this factor of 30, you don't want to put it with the 34, because the 34 is the scalar in the system. You want to put it with the negative 23. So if you take negative 23 and you multiply by 30, you will get negative 690, right? Times 34. And this is in mod 98, guys. Anytime you have a congruence notation, if you don't have a mod with that, it's really not making sense. So you need to keep writing. I know it's a little repetitive. You need to keep writing that down, the modulus. So this is in mod 98. And so what you see here is that x congruent to negative 690, mod 98, is a solution. So 34 times, here's my x value, is congruent to 60 in mod 98. Pretty easy. That's actually, if you wanted, we could call that our x naught. So that's sort of the first one. We specifically found x naught as our solution. And to find other solutions, we now take these multiples of n over d. Now d is only 2 here. Okay, so it's not going to take it very long. There's only supposed to be 2 solutions. So I can take my x naught and I could subtract what would it be, 98 divided by 2? Right, so which is 49. So we can get a second solution. So another solution is, I guess I'll just call it x1, which would be congruent to negative 690 minus 49, which is negative 739. And this is in mod 98. Now, a couple of comments. First of all, there's nothing that says you have to live with these huge negative numbers. So remember, you can add 98 all day long to any solution and obtain another solution. So I would probably do that. I probably don't think of negative 690 as the best answer I could have given here. So you might want to add multiples of 98 to that. And I just kind of did this in my head. So then x naught, which is congruent to negative 690, turns out it's the same in the world of mod 98 as negative 4. Negative 4 would be a good answer to give. And you should be able to check it. Plug in negative 4 here. The difference between 34 times negative 4 and 60 should be a multiple of 98. And x1 could be thought of as, well, subtract 49. Now we'll subtract the 49 from this, and we'll get negative 53 mod 98. So these would be two non-congruent solutions. They're not congruent to each other in mod 98. Agreed? I mean, they're not far enough apart to be congruent to each other in mod 98. What do you guys think? Are there questions on that so far? Yes.
So we don't care about x naught and x1 to be between 0 and 97.
Was that gonna be your question? Okay, yeah, so if they said something like, give me the two smallest positive solutions, then you would need to add 98 to these to get the two smallest positive solutions. But if they said, give the two largest negative solutions, these would be the right answer. Yeah, so there is no, I mean, if you see a congruence equation like this, there is no right or wrong congruence class representative to give as an answer, right? So we have, 25 people in this room. We have 25 different x's that are all equally correct in the world of mod 98 because they're the same. It's only if the question gets more specific, like if this is supposed to be, the number of, cows on your farm or something. Okay, well now we wouldn't expect to have a negative answer. At that point, you'd have to figure out that, okay, it needs to be a positive number, and maybe there is some constraint that's provided. And yeah, I have been known to ask the question in that way before. Okay. Yes, Kim.
And the minus 49 came from 98 divided by 2, right?
Yes, n over d, right? N over d. The n is 98, the d is 2. Yeah. Now, here's the deal, guys. This is not the only way to express the answer. The fact that the GCD of A and N divides B actually means that there is a common factor of whatever that D is. There's a D inside of A, there's a D inside of N, and there's a D inside of B. So if you said to yourself, you know what, I don't want to deal with the numbers this big, I'm going to take the entire congruence and divide it through by 2. That would be legit. That would be totally fine. So just as a quick side note here, I'm just going to point out an alternate solution to this. And what we just did is not wrong. Let me be very clear. This is totally good. But if we wanted to, we could divide the entire congruence through by D. Okay, we could divide it through by D. And of course, in this case, the D was equal to 2, just to remind you. So in this case, we would divide the whole thing through by 2, including the modulus, everything. So it would become 17x congruent to 30 in mod 49. Right. Yeah, so we could do that. And now the numbers are smaller. The new GCD for this system is 1, right? The GCD of 17 and 49 will be 1. Obviously, that divides 30. So we could just solve this congruence. This time, there would only be one mutually incongruent solution, but it would be in mod 49 rather than mod 98, right? Yes.
From that one solution in this congruence class, will we still somehow be able to get the class of?
Yeah, I'm gonna show you that.
Okay.
You're getting ahead of me. Yes, I'm gonna show you that. I actually would like to solve this one and just see what the answer is as to how it compares to the two answers that we got here. Is somehow, now we're only gonna get one answer over here, but the thing is the modulus is cut in half. Right? Actually, if you worked in the world of mod 49, these would be the same. And so in mod 49, sure, -4 and -53 is really the same single solution. So this system, this congruence has one solution in two solutions in mod 98. But that can be combined into one solution in mod 49. That's my point. Yeah, 10.
On the homework, are you okay with either solution?
Either solution, absolutely, absolutely either solution. I actually find most people generally prefer this because the numbers are smaller.
Yeah, just the question says mod 98, so I don't know if I'm supposed to stick with that.
It's the same. I mean, if you gave me a solution in mod 49, I would be able to list out what all the X values are. And that's ultimately what matters. So yeah, it's just a different way of representing the solution. So what you would do here is, the same thing. You would take 49, you divide it into 7. I'm going to go ahead and do this if you don't mind. I'm going to go ahead and quickly run my Euclidean algorithm. I'm going to go fast though. Hopefully not too fast. So I'm going to divide 17 into 49. It goes 2 times with a remainder of 15. Then I take 17, divide by 15. I get a quotient of 1 and a remainder of 2. Then I have 15, which is 7 times 2 plus 1. All right, now I'm going to come over here on the other side and run my algorithm backwards. Starting from 1, I get 15 minus 7 times 2. I'm going to replace the 2 by 17 minus 15. I'm going to clean that up real briefly. So it's going to be actually 8 factors of 15 minus 7 factors of 17. And then I'm going to take the 15 and rewrite it as 49 minus 2 times 17. And then minus 7 times 17. And I know I'm going a little fast. I'll stop in just a second, let people catch up. But this is 8 factors of 49 minus 23 factors of 17. Yeah. Okay, so let's come back here and let you guys catch up for a second. Let me know if I made any mistakes. Always a little stage fright element up here for me. I hope I can do the math correctly. Supposed to have gone to school for math for a long time. So hopefully I can get the numbers right. Yeah. Anyway, I think I'm so far so good. So in the world of mod 49, I'm going to do just like I did before. In the world of mod 49, we have a 1 on the left side. And then on the right side, we have a 17 times a negative 23. And this is in mod 49. Yeah, in mod 49 like that. This time, instead of jacking the result up by a factor of 60, like I did earlier, here, I only multiplied it up by a factor of 30 here, 60 over 2. Here, I still have to jack it up by a factor of 30. So if I do that, so that doesn't actually change. So multiply by 30. And we'll get 30 is congruent to 17 times negative 690 in mod 49. So what you see is I'm getting the same x naught that we found before. Right, so X naught can be taken as negative 690. And this is in mod 49 this time. And so, of course, that makes sense that essentially, so this would also be congruent to whatever I reduced it to, -4 in mod 49. So this is the only solution I'm going to record this time. Because I don't need to write down the -53 that we had because that's equivalent to -4 in mod 49. If we stick with mod 98, we have to list both solutions. Everybody seeing the difference between like, I actually think it's easier to reduce this modulus down. If you find out that D divides B, which is what is required for there to even be a solution, then you ought to be thinking to yourself, oh, that means I can divide everything through by D and just make the numbers all smaller. Actually, the book states this result as a kind of as a corollary, and I think it's probably worth writing it down. Are we okay on this, by the way? Make sense? Okay. So the corollary here that the book has basically is, so if the GCD of A and N is 1. Now, what I just got done saying is, well, if it's not 1, if it's equal to D, and if D does divide B, you can divide the congruence through by D so that, like here, the GCD of the A and the N is equal to 1. So in other words, what I'm saying is this can always be arranged. Even if your original congruence isn't presented this way, you can fool with it by dividing through by whatever common factors you find so that this is already going to be true. And in this case, if that's the case, then the congruence AX congruent to B mod N has a unique solution. Emphasis on unique. It is a unique solution modulo N. Yeah, that's the point. A unique solution modulo N. And we've pretty much just illustrated how it works in this alternate solution that we just did. If you want to have a little bit of an abstract description of this, it's not just with specific numbers in it, just to give you sort of the, I guess I'll call it a strategy here. We'll make this really brief. The strategy for that corollary is that, well, you start off by writing your GCD as an integer combination of A and N. That's the early Bouzoux's identity result that was in the videos way back at the start of the semester. So what you basically do is you write 1 as an integer combination of A and N. Let's just say I'm going to write it as A times R plus N times S for some integers R and S. So you start off just doing that. And then you really want to have a B here. So you just multiply through by B. So multiply by B. Okay, so that's B equals ARB plus NSB. And now you just reduce mod N. So mod N, well, this is still a B. I'm going to turn the equals into a congruence now. I'm going to have my A here times RB, and the NSB is actually just 0 in mod N. So if you're looking, this is in mod N. If you're looking for what is X, there it is. So that's kind of a streamlined description of kind of how that process works out. Yeah. Does this make sense? So just to take it again from the top, if I have any old congruence like this, the first thing I can do, well, first I check if the GCD of A and N divides B. If it does, I remove all common factors, right? And in so doing, I basically end up with a congruence that has this property. So you divide out by that D, that D that was originally in common to the A and N. You end up with a congruence of this form, and then you're going to report your answer as one unique solution in mod N, right? And here's how you come up with that solution. So it's all kind of in one place for you, how that entire process works. Pretty neat. I love it. Questions here? Okay, there's only so much you can say about linear congruences. They're just not that interesting enough to have that much to say. So I think I'm going to move on to a new topic. This should be everything you need for the homework for Friday at this point. This just lasts a little bit, comes up a little bit in the last section, but I'm going to start talking about something that'll be for the following week, which is systems of congruences. And this really, if some of you have been kind of muddling along as if, well, this is all, I've kind of seen this before, 302, whatever, congruence theory and divisibility and all that stuff. I'm going to move into something now I'm pretty sure you don't do in 302. And that is, in Math 302, you don't talk about systems of congruences that you want to simultaneously solve. So let me state that as a problem. So well, maybe a question first of all. What about systems of congruences? This is actually still in chapter 4, but it's kind of moving on to the next thing. So the problem, if I can just state it as a problem for us to ponder for a minute, is that we would like to find integers. I'll call them x again. So x is an integer. Find integers x such that, and then I don't just have one congruence, I'm going to have a whole slew of them, and I'm going to label this list of congruences with a star for your notes, because I'm going to keep referring to it. And I'm going to start off a little bit easy in that I'm going to assume that I've already got my congruence solved for x. So my first congruence might be x congruent to A1 in modulo N1. Now, if my original congruence is, this, if that was one of my congruences, then before I could even write down the first equation in my system, I would have to take this one and solve it for what x was literally itself congruent to in that modulus. So you might actually have to do all the work we just showed just to get to this equation. But then what if there are other equations? What if we also want x to be congruent to, let's say, A2 in mod N2? And I'm just going to go dot, dot, dot. We don't know how many of these we have, but there's maybe a whole series of these. And just to use the book's notation, I think the last one is going to be x congruent to A sub r. And this would be in mod N sub r. So this is the problem. Can we find an x that sort of simultaneously solves all of these, right? Solves all of those at the same time. Of course, question first. I don't have any assumption about that yet. I'm going to make some for the moment, I'm just stating this is a very broad problem, but there will be a reason why we need them to be pairwise relatively prime very shortly. So you're kind of getting into what I was going to say, which is that there's no guarantee that this system would even have a solution. Just like with the linear congruences we were just talking about, there's a requirement that has to be met first. And the same thing is true here. So just as a note, such systems may not have a solution. I suppose I should give a counterexample. And so you could see one that maybe would convince you that it's not always going to be possible to have a solution. So for example, if I told you that x needed to be congruent to 2 in mod 3, and the second equation in my system, maybe it's x is congruent to 1 in mod 6. So we gotta have sort of something like that. So you're looking for x's that are congruent to 2 mod 3, but also congruent to 1 mod 6. The first equation tells you that 3 has to divide x minus 2. But the second congruence tells you that 6 has to divide x minus 1. But of course, 3 divides 6 also. So now you're telling me that x has to, x minus 1 and x minus 2, they both have to be multiples of 3. That doesn't sound too good, right? 2 consecutive integers are not going to be multiples of 3. So this has no solutions. I think this is what, Ken, you were getting at. I've chosen an example where the moduli, which are 3 and 6, they are not relatively prime. So if we want to guarantee that our system has a solution, we will need to assume that the moduli are all pairwise. It's called pairwise relatively prime, meaning any two of them at a time are have no common factors. That's going to be what's needed to guarantee that this would have a solution. So if the moduli are, again, pairwise relatively prime, okay, does everybody understand what I mean by that? So I mean, if I take the numbers 2, 3, and 4, there is no common factor of all 3 of these numbers, okay? But that's not what I'm talking about. Pairwise relatively prime means any 2 of them considered in isolation should have no common factors. So these numbers would not be pairwise relatively prime, even though there isn't any number other than 1 that divides all 3 of them, right? So just to be clear about what pairwise relatively prime means. But if the moduli are pairwise relatively prime, we are guaranteed a solution. Yes.
That solution is unique, right?
I'll talk about that in a minute. It will be unique in a certain sense, so I need to explain it very carefully. Yeah.
Do we require A1 to be the unique solution, or could it be any other solution?
It won't necessarily be A1.
But I mean, like, just looking at X congruent to A1 mod N1, so that on its own, does A1 have to be the unique solution?
No.
No.
No. So when we say unique solution, so I haven't even talked about this solution being unique yet. I just said I guarantee that there is a solution. So you guys are quick. You give me a chance to spit out my theorem. I mean, we have to specify a modulus for that. Like, so this X naught here, this was a unique solution in mod 49, but if I said, well, what about in mod 98? Then I said, oh no, this wasn't a unique solution. There were actually 2 solutions, right? So the uniqueness is going to hinge on the modulus. I'm going to have to say there's a unique solution modulo something, right? That's going to be the way this is going to end up being phrased. And but there is going to be a uniqueness statement if anybody is wondering, and we're going to state it now. Does anybody know what this is called? This is a famous problem. I don't know if you've seen it anywhere else. Oh, good. Then we'll make sure we never get rid of the number theory class. I went to a department meeting on Friday for our faculty. As many of you know, we have a lot of math education faculty, and as of now, the math ed majors have to take a certain number of these 400 level courses for their major. Well, these math ed people are, I love all of them. But they are sort of deciding to make their own new courses for their own concentrations. And so I was sitting there looking at Dr. Murphy, and Dr. Murphy was looking at Dr. Rathbun, and we're all sitting there thinking, what's gonna happen when all these students stop taking our classes? Because they're gonna take away they're gonna basically have the math education majors take this new curriculum of courses, which is probably great. I mean, I think it's wonderful in some ways. But then we're all of us pure mathematicians sitting here thinking, well, we're gonna be like fighting for the scraps of which pure majors are left. And then Dr. Glesser, who's department chair, says, oh yeah, we'll have to be cutting some of those courses. And we really started looking at each other then, like, which course are we gonna get rid of? It better not be number theory. And I was like, I was trying to think, okay, what is there in Math 430 that they're not gonna see anywhere else? And you guys just proved it for me, because you haven't seen this result and you wouldn't have seen it in any of those other courses. It's the Chinese remainder theorem. It's a very, very famous result. So I'm going to state that here, the Chinese remainder theorem. I was shocked to learn that for the department to break even, like money-wise on a class, there has to be 26 people enrolled. And I'm thinking like, and actually this class is the highest enrolled 400 level pure math class this semester. So if you look at whatever it is, 450 and 407 and so on, they all have less enrollment than this one, and we're not even at 26. So I'm starting to get, so guys, you got to find 2 or 3 buddies that are going to become math majors. And if they're pure math, extra credit for that. I got to keep my job. I'm getting a little nervous now. Anyway, fortunately, it's the 26 thing is only like averaged over the whole department. So we have like, you know, like math 110. I don't know, they probably have 50 people in each of those classes. So by keeping those classes around, our average is still good. So we're good to go for now. But anyway, we've been put on notice that these courses could have to be downsized a little bit.
Do you know when they'll decide that?
It'll be a little while.
Okay.
Yeah. I'll try to slow down this process with the math ed faculty, at least until I retire. Then I don't care what they do. Anyway, yeah.
Would one state that if X is converted to A mod M1 and X is converted to B mod N2 when N1 and N2 are relatively prime, then X is converted to A times B?
It's not A times B, actually. Actually, when I state this theorem for you, we'll actually write down what the solution is, right? It will have all of these A's in them, but it's not just multiplying the A's together. It's much more complicated than that. So let me actually state this, and then we'll prove it actually as well. This is one of the big results in number theory that you don't get to see in any of those other classes. So I'm going to state it here. Let's let N1, N2, and ... up to NR. These are all going to be positive integers. Such that the GCD of Ni and Nj is equal to 1 for all I not equal to j. Okay, so then the system, which is the system star, that's why I had you label the that system of congruence as a star. That system star has a unique solution . Guys, what I really want to impress upon you is that if I stop right now and I say it has a unique solution, it is not a well-defined statement, right? I have to know under what modulus, right? So modulo, it's a unique solution modulo the product of N1, N2, and ... up to NR. So you're multiplying the individual mods together, okay? So if the moduli are not pairwise relatively prime, then we're not gonna be able to use this Chinese remainder theorem. We're not gonna have a unique solution modulo the product. We might not have any solution, as we've already seen. So this is very critical. Let's do the proof of this. The proof is actually in the proof. And by the way, there's a number of different proofs for this, but the one that I like to give is the one that actually constructs the X solution for you as part of the proof. Okay, so this proof is kind of a constructive proof where you get your solution in the midst of doing the proof. Okay, so here is what we're going to do. We construct a solution to star as follows. So what I'm going to do is I'm going to create a little notation here to make things a little nicer. I'm going to just let n be the product of all of these moduli, n1 times m2 times ... up to nr. I'm just going to use that. And here's what we then have to do. So we create this little n, which is the product of those individual mods. And then for each k, which goes from 1 to 2 to 3 and ... up to r. So for each k between 1 and r, we're going to let capital N sub k be equal to the little n that we just created divided by the little n sub k. So if you're wondering what that really means, you're just taking all of the little n's and you're dividing one of them out. So it's as if you sort of multiplied all of the n's except for the kth one, kind of skipped over the kth one. If you want to think of it visually as that product.
Sort of like that problem from section 3.2.
Yeah, I know what you're thinking of. It's exactly like one of the homework problems from last week where you had all of the primes in that case, except for one being multiplied together. Yeah, that's very good memory of that as well. I was thinking the same thing. So we're gonna create this capital N sub k. And I want you guys to notice that the greatest common divisor of the n sub k, the big N sub k, with the little n sub k. Let's think about common factors here. Remember, guys, little n sub k is relatively prime to all of the other little n's, right? GCD of any two of those is 1. So this little n sub k has no factors in common with any of the other little n's that are actually what make up the big N sub k. So this GCD, my friends, would therefore just be 1. Because there's no common factors between this little n and any of the other little n's, which is what the big N is made out of. Okay, so if that's the case, so thus the congruence, which is big NK times y sub k, congruent to 1 modulo little n sub k. So here's a linear congruence. Let's just remember, so this is the way we were writing the linear congruence just a few minutes ago. And the point was that as long as the GCD of A and N divided B, we were good. There was going to be a solution. Well, the GCD of big NK and little nk is 1. And so, of course, 1 divides 1. And so this congruence has a unique solution, has a unique solution. The unknown here that we're solving for, by the way, is the y sub k. It has a unique solution, I'll call it y sub k, and that would be modulo little n sub k. I'm just using this thing, just using the corollary. So this is by the corollary above. Hopefully you'll recognize that I just mean the previous corollary. by that previous corollary. Okay? Is everybody with me? Because now I'm ready to tell you what the X is that solves this system star. I'm ready to write it down, then we're gonna have to check that it works, and then we're gonna have to check that it's unique modulo the product of the ends. So there's still some work to do here. But we've got all of the setup now for this. Notice that you have to solve R linear congruences in order to get all these Y values. So this can take some time. It could get kind of brutal to have to do too many of these. But the claim now, the claim that we're going to make, this is really where we're headed, is that we can write down our unique solution in terms of the Y's, the A's, and the big N's, right? We can do all of that. So let me write it down. X congruent to A1, big N1, Y1, plus A2, big N2, Y2, and plus dot, 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 plus AR, big NR, YR. That, in the world of mod N, is a unique solution to star, to our system star. This is going to be a unique solution to star. Which is what the theorem is telling us. The mod N, remember this is N now in my new notation, the product of all those little n's is it. So this is what we mean when we say that the proof basically constructs the unique solution right within the proof, right? It's all right within the justification of the theorem. This is one you're going to want to memorize. You're going to want to know what this claim is. Let's just check this claim. As usual, there's a uniqueness statement and also existence statement. So the first thing, I actually have a couple of things I need to check. I need to check that that X really does solve all of my congruence equations, right? So check that X satisfies star. I got to check that. That's one thing I need to do. I have a feeling if I just check the first one, you'll get the idea by symmetry that it will check all of them because it's very symmetrical the way this is constructed. So let's just check it. So let's just consider the first congruence. The first congruence is being viewed, so we have X, right? So X was congruent to A1, capital N1, Y1, plus A2, capital N2, Y2, plus dot, 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 plus AR, capital NR, YR. If I look at it in mod N1, so I'm just focusing on the first congruence, which is in mod little n1. Do you guys all agree that in mod little n1, the big N2 is 0, and the big N3 is 0, and the big N4? Because take a look, your big NKs have all of the little n's in them except for the K point, right? So in other words, this big N2 has a little n1 inside of it. So this is a multiple of little n1, meaning that it's 0 in that modulus, right? So this is essentially congruent to 0. And the next one will be congruent to 0, and so on and so on and so on, congruent to 0. What I'm trying to say, going to be a little long-winded, sorry about that, but it's really just that the first term is the only one that doesn't get zeroed out. It doesn't get zeroed out. So that's mod n1 still. I'm still working only on the first congruence.
And we already know that N1, Y1 is congruent to one mod.
Yeah, I'm gonna use this one, guys. Sorry, I put a box here. Big N1 times little y1 is congruent to 1 in mod little n1. So the big N1Y1 goes away and you just get A1 in mod N1. That checks that first congruence. And then what we can say is we can just say all of the other congruences are similar, right? So proceed similarly with all other congruences in star. So that checks this first claim. The X does satisfy the whole system. It satisfies this equation, this equation, this equation, this equation, satisfies all of them, right? The only thing that hasn't been done yet is verifying the uniqueness of the solution, that you can't have another one. And that actually turns out to be very easy. So let me show that. Maybe here, we can write this one down. By the way, where the name of this came from, it was back in war times in China, and they had the army, and of course, sadly, people died in battle, and the generals wanted to know, how many of their troops had survived some skirmish or battle or something as part of, some pretty ancient. I mean, this is an old result, hundreds of years old, but back in the old days, they said, well, it's very hard if you've got like a whole army of people standing around and you're trying to count how many people you have. It's very hard to do that. I don't know if you've ever tried to count a group of people in a room, but if people are not organized very well, it's kind of hard to do that. What you can do is you can say, all right, everybody get into groups of 3. See how many people are left over. Everybody get into groups of 5, see how many people are left over. And you can choose different mods. That's basically what you're doing. And you're looking at remainders in those moduli. And then you can say, well, I know I have, somewhere between 400 and 500 troops. Okay, so then you can find the unique solution that's within a certain range, essentially using this result. It's kind of where the name came from. Kim?
Is that why the Chinese have like the apparatus, the thing that like helps with the numbers, the apparatus?
I don't know about that for sure. I don't want to say something I'm not sure about, but I know what you're talking about. That old.
Especially if they do it in modern.
Okay, yeah, I am not 100% sure if there's a connection there or not. I'll look into that. It's an interesting thought, but yeah, definitely this result is named from a pretty old story about trying to count things in a case like after a battle or something. What did I say? Oh yeah, I gotta check the uniqueness. Still doing the proof here, guys. At some point, I'm probably gonna ask you guys to learn this proof. I mean, I will probably want you to know it. It's a really, really important result in number theory. So for the uniqueness, what we're gonna do as usual, I'm sure you've done it many times. Suppose there's another solution, okay? So suppose that Y is also a solution to star. In other words, what we're saying is that Y is congruent to A1 mod N1, and Y is also congruent to A2 mod N2, and so on and so on. Yeah, just like that. And so Y is congruent to AR mod NR. But X was already congruent to all of those same things, right? So thus, X and Y are congruent to each other. Well, let's just make it really explicit here. So X is congruent to A1, which is congruent to Y in mod N1. And then X is congruent to A2, which is congruent to Y in mod N2. And X is congruent to Y. I guess it's A sub R on the last one here. Congruent to Y mod n sub r. And so, I don't want to erase my statement yet, so let's just come over here. Well, if we subtract x and y, right? N1 divides x minus y, and 2 divides x minus y. I'm rewriting it as a divisibility condition. And so on and so on. N sub r divides x minus y. All of these are true. Every single one of them. So x minus y is a multiple of each of these little n's. In other words, it is a common multiple of n1, n2, n3, and so on. Okay, so let's write that down. X, we're almost done now. We're almost done with the proof. X minus y is a common multiple of n1, comma, n2, comma, dot, 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 comma, nr. But what do we know about the n's, the original n's? They're pairwise relatively prime. They have no common factors. They have no common factors. So this x minus y has all of the factors of n1 in it, and n2, and n3, and none of those factors are common with one another. So actually, x minus y will therefore be a multiple of their product, of their entire product. In fact, the LCM, if you wanted to say it that way, the least common multiple of these little n's is actually the product of all of those little n's. And x minus y is a multiple of that. Okay, so I'll just add that here. Since n1, n2, and dot, dot, dot up to nr are pairwise relatively prime, what we can say is that x minus y is a multiple of the product of all of these n's at that point. At that point, x minus y is a multiple of the product of the mods. And of course, the product of the mods is n. Well, if x minus y is a multiple of n, that just means that x and y are actually, in the world of mod n, the same. X is congruent to y in mod n. This other solution y that we thought we had started off, suppose we have another solution to star going along with the original x, which is a solution to star. Well, it turns out you didn't really have two different solutions. They're actually the same in mod n. Right. So there you go. That's kind of the way you can work with that. Make some sense? Okay. How much time do I have? 5 minutes? I know you're going to ask me about all sorts of variations of this, like what if there are coefficients in front of the x here, right? Or what if the mods are not pairwise relatively prime? Is there any hope of redemption that we could salvage some kind of result here? We're going to have to kind of save some of those things for Thursday. Maybe for just the limited time I have right now, I'll just do an example of this Chinese remainder theorem. Would that be a good idea? Yep. Okay, let's just do an example of it with some real numbers. I think I won't make the numbers too crazy, so this shouldn't take that long. Okay. Famous last words. Actually, I shouldn't erase it. This is what we need. Oh my God. Keep that up there for now. This shouldn't take that long. All the students roll their eyes. You've heard that before, Dr. Andrew. No, I don't think this will be too bad. Let's try it. Let's do this example. Let's solve x congruent to 3 modulo 8. X congruent to 4 modulo 9. And X congruent to 6 modulo 11. Now this will be reasonable, I think. Can get this done pretty quick. So really what you want to do is, well, first just confirm that the mods are pairwise relatively prime. They are. So our final answer, our solution will be a unique solution modulo the product of these. So you have to figure out 72 times 11. That'll be the modulus of your final answer. And the X is constructed right here. So all you've got to do, guys, is really just identify what everything is. So A1 is 3, A2 is 4, and A3 is 6. I'll just start off with that. Okay. And then the next thing to do is figure out your capital N's, because I see those in the formula as well. So just remember that each of the capital N's is the product of all of the other little n's, except for the one that is being subscripted. So capital N1 is the product of N2 and N3. And these are the mods over here. 9 times 11, so N1 is 99. And then N2 would be 8 times 11, which is 88. And N3 would be 8 times 9, which is 72. Okay? The only thing we have to work a little bit for now is to get these Y values. But I think we can do this pretty easily. So far, we've got all the A's, we've got all the N's. So for the Y1, right, I have to take so the equation is still over there in that box. The capital N times the little y has to be congruent to 1. So 99Y1 has to be congruent to 1 in mod 8. And the mod 8 part is what makes this nice, because you can, of course, take 99 and reduce it in mod 8. So let's do this in our heads, guys. We only have 3 minutes. Do it in our heads. So if we divide 99 by 8, I believe 96 is a multiple of 8. So 99 is actually the same as 3 in mod 8. If you don't believe any of this, just pull out a calculator. I'm going to do it kind of fast. The other thing I'm going to do, so the other thing, if I want to figure out what Y1 is now, instead of using the Euclidean algorithm, these numbers are so small. Remember, there's a unique solution for Y1 in mod 8. So if you wanted to, you can just try them all. But you can kind of see, Kim's already figured it out. 3 times 3 is going to give you 1 in mod 8. So this is a perfectly good time to just, by inspection, write down the answer. Okay, so Y1 would be 3 in mod 8. Okay, and then we do, for Y2, we take N2, which is 88, and times Y2, this should be congruent to 1 modulo little n2, which was 9. That one was 9. By the way, so if you take 88 and you divide it by 9, you're going to get a remainder of 7. But you're also allowed, if you just want to make your numbers nicer, you can use negative numbers. In mod 9, I don't care if you change a 7 to a -2, that's totally fine. Okay? Can anybody eyeball this one? What's Y2 going to end up being? Let's start giving extra credit for fastest answer. I think it's just 4. Okay, -2 times 4 is -8, which is congruent to 1 mod 9. So this one is just 4 in mod 9. Okay, so I got that one down. And then the last one is the N3 times Y3. So 72 times Y3 should be congruent to 1 in modulo 11. This one might be a little hard to do in our head. 72 reduces in mod 11 to 6. So obviously you can subtract 66 from 72 and you're left with 6. And we can do this in our head. Y3 is just 2, right? Okay, so that's in mod 11. And again, I'm saying I'm writing these results in mod because I'm pointing out you can add and subtract the modulus all day long to any of these y values and you'll get another acceptable answer. So what is our final x solution? Maybe I'll try and write it up at the top here. The x will be congruent to a1, which is 3, times n1, which is 99, times y1, which is 3, plus a2, which was 4, times n2, which was 88, times y2, which was also 4. And finally, the third one would be a3, which is 6, n3 was 72, and y3 we said was 2. And this is just plugging in all the numbers, right? That's all that's going on here. And that's what I have. And I worked this out. Since we're out of time, I'm just going to tell you the answer. It's 3,163. You can check me on a calculator for that. But that reduces in, so the mod little n, sorry, so the little n is 8 times 9 times 11, which is 792. So I can reduce this down. You don't have to. This is a perfectly good final answer. But I did reduce it down. Actually, it's interesting. It turns out it reduces to -5. And you probably look at the answer and say, oh yeah, duh. It works in all three equations really easily. So -5 is an answer. And this is in mod 792. Remember, guys, if you don't write the mod there, it might as well be wrong. Because I don't know what you mean by the answer. So you have to have the modulus in there as well. So yeah, so that's just a quick example. It's very computational. I could ask you for the smallest, or maybe the two smallest positive solutions, in which case you'd have to take -5 and start adding 792 to it a couple of times. That's that. Any questions? Everybody like this result? Kind of fun. I love the Chinese remainder theorem. You'll see some word problems in the homework about it. Just kind of neat. That'll be the next assignment. On Thursday, I'll talk about, as I said, some tweaks to this. You know, what happens if the mods are not relatively prime? What happens if you've got coefficients in front of these x's and so on? And we'll see if we can kind of generalize what we're able to do. So, but that's it for today, guys. Thank you so much for your patience and your time. I've really enjoyed it being with you, as I always do. And I will head downstairs, be down there most of the evening if anybody wants to talk about questions on the homework or anything else for that matter. All right. Have a great rest of your Tuesday. Can't imagine it getting better from here, but you can try. Thank you.